Welcome to week 11. This is lecture 51, the first lecture of week 11. So, as of now, we have talked about theories of optimization, we have talked about techniques of optimization, various techniques, unconstant optimization, linear programming, nonlinear programming with constants, etc. So, now in this week 11 and in the last week, week 12, we will talk about various applications of optimization as well as use of software tools for solving optimization problems. So, today we will start our discussion with applications of optimizations. So, now in the beginning of today's lecture, we will first talk about two MATLAB functions known as fminCon and fsolve, and then we will take an example to demonstrate the use of fminCon and fsolve to solve an optimization problem which is taken from chemical engineering area. So, let us start with applications of optimization. Mostly we will take examples from chemical and biochemical processes. So, first let us start with use of fminCon solver. fminCon is basically a solver for nonlinear programming problem, and it is a part of MATLAB's optimization toolbox. fminCon can solve a general nonlinear programming problem with constants, and the problem that it can solve is shown here. So, we solve a minimization problem. So, if you have a maximization problem, you have to convert it to minimization problem by taking minus sign. Note that all the constants are of less or equal to type or equal to type. So, the problem is minimize fx such that cx less or equal to 0, c equal to 0, ax less or equal to b, a equality x equal to b equality, and x is bounded between lower bound and upper bound. So, c of x less or equal to 0 is basically nonlinear inequality constant. C equality x equal to 0 is nonlinear equality constant. Ax less or equal to b is linear inequality constant. A equality x equal to b equality is linear equality constant, and x is bounded between lower bound and upper bound. So, you can write bounds on decision variable x. So, x is a vector of decision variables. Fx may be nonlinear objective function. So, this is the kind of problem that MATLAB's fminCon will solve. So, if you can cast your problem in this format, MATLAB can solve this optimization problem for you. So, we will see how it does. So, what is the syntax? So, the syntax are shown here. So, you first have to define a function where you will write down the objective function. So, the function fun will return the value of the objective function at the decision variables to the fmincon solver. So, you have to supply this function. So, you have to write an M file where the objective function will be evaluated. X0 is the starting point, A and B comes from linear inequality constant. So, A is the coefficient matrix, X is the vector and B is the right hand side vector. So, if you do not have any other constant, your syntax is this. If you have linear equality constants, then you have to add these two. That means, this is for, so A underscore EQ is basically the coefficient matrix for equality constant. So, this is equality. So, if you do not want to supply bounds on x, you use syntax up to this. Next, if you want to use bounds on decision variables, you use this. Now, your optimization problem may involve nonlinear constants. In that case, similarly to objective function file, you also have to write another function file where you will mention the nonlinear constants. So, this is for nonlinear constants. So, I have given name non-L con. You can give whatever name you want. So, idea is that you have to supply a function where you will write down the nonlinear constants associated with the optimization problem. Note that this function needs to be supplied separately, it has to be written by you. The linear inequality constant and the linear equality constant can be put in a standardized form. So, that is why it was possible to take care of linear equality constant and inequality constant by supplying the coefficient matrix and the right hand side vectors, namely A, B, A equality, B equality. But the general nonlinear constants can take any different form. So, you have to supply a function where you will define the nonlinear constants. Then we have also seen the use of options before. So, you can also give options as input where you will tell the fmincon solver that you want to say display the results of each iterations, you want to change the tolerance, you want to choose a particular algorithm, so that fmincon will use that particular algorithm only, so on and so forth. Now, here we have seen we have written the output of the fmincon is only x, that is the decision variable, that is the solution of the optimization problem. But you can also have the function value at the decision variable. You can have exit flag, which will tell you about how whether the solution you obtained and the convergence was achieved for the solutions or not. So, it will tell you about how the algorithm solve the problem that you have supplied. Similarly, output gives you various information about the algorithm, such as number of function evaluations. It tells you about what algorithm it used, so on and so forth. Lambda, it gives you the Lagrange multipliers, the gradients at the decision variables solutions, also the Hessian matrix of the function evaluated at the decision variable solution x. So, the complete syntax will be this for the left hand side and this for the right hand side. So, this part and this part. Note that this last part. You can obtain more information about the use of fmincon from the MATLAB website. Now, let us take a quick example on the use of fmincon. We want to minimize the function x plus y subject to x square plus y square equal to 1. So, you have a simple linear objective function with one nonlinear equality constant. So, that is the problem. So, first thing will be to write a function file for the objective function. Objective function is minimization of x plus y. So, this is the function file that I write. So, you have to write the function file in this format, function f equal to, I have given the function name as func. You can give any name you want, say my function, etc. X is the decision variables. So, they are the trial vectors for the solutions. So, this is a vector which contains this x and this y. So, x equal to capital X of 1, y equal to capital X of 2. So, f, the objective function, is nothing but x plus y. So, while fmincon will solve this optimization problem, it will send the trial vectors x, which contains small x and small y, to this function file func func, and the value of the objective function f will be evaluated and returned to the fmincon solver. Okay. So, I have only linear equality constants, sorry, nonlinear equality constants. I do not have linear inequality constant, I do not have linear equality constant, I only have nonlinear equality constant. I do not have nonlinear inequality constant, I have only nonlinear equality constants. So, you have, so those A, B, A equality, B equality are not relevant for me. So, they are not present, but I have a nonlinear equality constant. So, I have to define a function for that. So, I am defining a function nonlinear for this nonlinear equality constant. Note that you have to supply a single function for both nonlinear equality and nonlinear inequality constant. So, look at the format of the function. How this is how you define the function. Output of this function is C and C eq. So, C for nonlinear inequality constant and C eq is nonlinear equality constant. So, I have only nonlinear equality constant. So, C is null matrix for me. C is not required for me. So, I have given this as the name of the function that defines nonlinear constants. We have to define two outputs for f min con, the nonlinear inequality constant which is C and the equality constant which is C eq. So, these are those two constants. For me, this I do not have in the problem, this I have. So, again this x contains small x and small y for the problem. So, those things are defined and the nonlinear equality constant x square plus y square equal to 1 has to be written as x square plus y square minus 1 equal to 0, because if you remember the first slides it was written as C eq equal to 0. So, you have to express the nonlinear equality constant as C eq equal to 0. So, C eq will be x square plus y square minus 1. So, once we have done this, we can now call f min con solver to solve this problem. So, I did not have A. So, A is null, similarly B. This capital A for A, capital B for small b according to our previous notation. So, I do not have linear equality constants. So, they are also null. Lower bound, upper bound I am not specifying. Let us say initial case is small x equal to 1, small y equal to 1. So, x 0 is basically small x small y which is 1 1. This is supplied initial guess. Now, you call the f min con solver. Note that this sequence is very important. You must supply all the arguments strictly in this sequence. So, when you do not have A, B, even then you have to define like this. So, now you write this statement on the MATLAB command mode and press the enter, or you can create a script file, M file, there you can write this statement and then run that M file. So, if you do this, you will get this as output. So, the MATLAB will return the solution of the optimization problem as x equal to 0.7, x equal to 0.7071 and y equal to 0.7071. So, x equal to y. This is the function value. These are the Lagrange multiplier. This structure will contain the Lagrange multiplier information. This is output, tells you about step size, algorithm, function count, etc. Now, next let us take another example. Now, this time the use of fsolve. The MATLAB function fsolve solves a system of nonlinear equations as represented by fx equal to 0. So, basically fsolve solves a system of nonlinear equations. So, it will find out x vector for which f of x equal to 0. So, fsolve is a part of MATLAB optimization toolbox. The syntax are very simple. X equal to fsolve, then you have to supply the function where you will write the equation that you are going to solve, and then you have to supply the starting initial guess vector. You can also use options to supply specific instruction to the solver fsolve. You can also have these as outputs. Apart from the solution vector, you can have the function value at the solution vector as fval. Exit flag will tell you about the termination criteria, whether it was terminated successfully. Output will give you informations about our optimization algorithm, function number of function evaluations, etc., and it will also give you the value of the Jacobian. So, all these things are possible. fsolve uses trust region dogleg as default algorithm. It can also use trust region and Levenberg-Marquardt algorithm. If you want to use Levenberg-Marquardt algorithm or trust region algorithm, you have to make use of option to tell this information to the solver. Now, let us take a quick example. Let us say I have these two equations which needs to be solved simultaneously, two nonlinear equations starting from -5, -5. So, first thing we write an M file that will compute the value of the equations at x, the trial solution. So, this is how I write that. I define the function. Look at the function definition, function f equal to myfun of x. So, x contains x1 and x2. So, you simply write the first equation as well as the second equation. Now, we call the optimization routine fsolve. First, you supply the initial guess x0 equal to -5, -5. You can supply options through optimset display iter, that means every iterations will be displayed or you may not want it, and then you call fsolve as x fval equal to fsolve at myfun x0 options. So, this is the syntax that has to be used and this is how we call the optimization routine. More information can be found at MATLAB website. Now, if you do this, you will get the solution as 0.5671, 0.5671 for x1 and x2. So, this is how you can use fmincon and fsolve. Now, we will take an example from continuous start tank reactor in series. We are asking what should be the volume of each reactor so that the conversion of a reactant is maximized. So, you have reactors in series. So, you have 3 CSTR in series. In these reactors, a reaction that consumes component A takes place. So, a reaction A to products takes place in each of these CSTRs. The volumetric flow rate to each CSTR is same F0, but note that the concentration are all different. Inlet concentration to reactor 1 is Ca0 and then here the reaction takes place A2 products. So, the concentration of the stream that goes from CSTR 1 to CSTR 2 is Ca1, here also A2 product reaction takes place. So, the concentration of the stream that goes from CSTR 2 to CSTR 3 is Ca2 and here also A2 product takes place. So, the concentration that comes out of the stream coming from the CSTR 3 is Ca3. So, reaction constant K are given, volumetric flow rate is given as 2 meter cube per hour, that is same for each reactor. Feed concentration of reactant A is 1 kilomole per meter cube. So, what is known is the reaction constant, the flow rate of the streams to each reactor is known, feed concentration to CSTR 1 is known. What are unknowns is the volume of each CSTR V1, V2, V3 and also the concentration, exit concentration of CSTR 1, CSTR 2 and CSTR 3, that means Ca1, Ca2 and Ca3 are all unknown. The objective is to determine the volumes of the reactors 1, 2 and 3 that minimize the concentration of reactant A at the outlet of the third reactor. So, we want to minimize the concentration of A here, that means we want the maximum amount of A to be converted to product B. There is a constant that the volume, that is sum of the volumes of all 3 reactors must be less or equal to 7 meter cube. So, V1 plus V2 plus V3 must be less or equal to 7 meter cube. So, the optimization problem is that find out the volume V1, V2, V3 such that Ca3 is minimized, at the same time V1 plus V2 plus V3 less or equal to 7 meter cube is satisfied. So, first thing is to do the modeling of this CSTRs in series. So, you write down the mass balance equations. So, mass balance equations, this is steady state operations. So, amount of A that comes in to a reactor minus the amount of A that goes out of this reactor minus the amount of A that is consumed will be equal to 0. So, we can write this as mass balance equation for each CSTR. F0, say for CSTR 1, you can write as F0 Ca0 is the amount that goes in to CSTR 1 with the inlet reactant stream. Then what goes out from CSTR 1 is F0 Ca1, and what gets converted to product is RA1 V1. Similarly, we can write this for CSTR 2, CSTR 3 as well, and in general they can be written as shown. So, reaction rate constants, reaction rates are given as RAI equal to K CAI to the power 1.5. So, K is given as 1, F0 is given as 2, Ca0 is given as 1 in appropriate units as shown. So, you can write down these 3 mass balance equations for CSTR 1, 2 and 3, and these are the reaction rates. So, this completes my modeling. So, now the problem formulation then will be minimize Ca3, find out V vector which involves V1, V2 and V3. Subject to these model equations along with the rate equations and these linear inequality constant. So, I have a minimization problem where I am minimizing Ca3 subject to the model equations which are all equality types and one linear inequality constant V1, V2, V3, V1 plus V2 plus V3 is less or equal to 7. So, you can solve it using F-min-con. So, first we write the model equation of the system in a function file. So, this is the function file where I am writing down the model equations. Note that I have defined this decision variable V as global variable, so that it is visible to other functions that I am going to write for the same problem. So, if the variable is declared as global, this will be accessible or visible to all other associated programs for this optimization problem. So, you define the parameters and the variables. So, these are the equations for the 3 reaction rates and these are the 3 equations for the 3 mass balances in CSTR 1, 2 and 3. So, now our objective is to find the CSTR volume that will minimize the concentration of A in the exit stream of CSTR 3, that is CA3. So, now we have to solve these CSTR model equations to find the concentrations CA1, CA2 and CA3. So, my unknowns are V1, V2, V3, CA1, CA2, CA3. So, the fmincon solver will try to find out the minimum value of CA3 by trying various values of V1, V2 and V3 while satisfying all the constants and satisfying the model equations as well. So, we need to solve the model equations for given V1, V2, V3 that the fmincon solver will supply. So, you need to solve the model equations and define the objective function in another function file. So, this is that function file. So, function f equal to obj fun volume. This volume contains basically V1, V2, V3. So, again we have defined the variable v as global, you see. So, it is visible in that CSTR function as well as this obj fun function. And now, if you note the model equations, these model equations are nothing but equality constants. These model equations are nothing but a set of nonlinear equations. So, a system of nonlinear equations. So, system of nonlinear equations can be solved by fsolve. So, that is what in this function value, in this function file where I am going to determine the objective function value, I am calling fsolve with an argument for that function to solve for CA1, CA2 and CA3, and I am getting CA3 as the objective function value. So, the initial guess for fsolve is 1, 1, 1. That means, V1 equal to 1, V2 equal to 1, V3 equal to 1. So, this function file which basically supplies the value of the objective function, it solves the model equations which are nothing but a system of 3 nonlinear equations by using fsolve. And then we take, so fsolve will return this CA which has CA1, CA2, CA3 all the concentrations. So, I take CA3 as CA3 is the exit concentration of CSTR 3. So, concentration of A in the exit stream of CSTR 3, that is what we want to minimize. So, that is my objective function value. So, once we do this, we have defined all the necessary functions. Now, I can call fmincon using the usual syntax. So, this is my say initial guess for volume V1, V2, V3. So, this initial guess was for fsolve. This is CA1, CA2 and CA3. Now, this initial guess is for fmincon. These are the initial guess for volumes V1, V2, V3. So, this is A and B, those Ax less or equal to B, which says that V1 plus V2 plus V3 has to be less or equal to 7. We do not have linear equality constants, we do not have bounds. I am sending an options. So, this is how I now call fmincon. Note that I do not have any nonlinear equality constants. In fact, the model equations are nonlinear equality constants, but that I am taking care of by solving using fsolve. So, then I just display the results. If we do this, we will get the solution as V1 equal to 2.07, V 2 equal to 2.33 and V 3 equal to 2.59, and the optimal value of Ca 3 is 0.210472. So, this is the optimal solution. So, with this you can make use of FMINCON FSOLVE to solve an optimization problem related to chemical reaction engineering, reactors in series. So, with this we stop lecture 51 here.